I'm not a mathematician, I'm only an amateur. I did a presentation for our homeschool collective a year ago, and I have a lot of personal research material left over, and I wanted to make some of it available. With the internet these days, you can find so many cool graphical representations. You can find the Moebius strip. You can find a illustration of what pi represents. As it goes around the circle, it makes it more easy to understand. This is called the Lorenz Attractor. If you want to look it up, I just put it here because I like the way it looks. But I understand it has a great significance in statistical analysis. It's a cool model that you can find on the internet. You know, sine and cosine are descriptions of angles, and this kind of shows you what it's talking about. It's really cool, isn't it? But wait, there's more. Math in music. This is where the math starts coming in. This is where the math geniuses can tell you why the harmonics of music sounds like it does, because it harmonizes. It literally harmonizes, and it's literally a clean and easy ratio that makes music sound good. And this is it, graphically represented. If you could imagine a guitar laying over this diagram and the bottom of the diagram representing the bottom where the pegs are being held and the top representing the nut, and then when you bang the string it makes a sound, doesn't it? But right in the middle of the sound, usually right around the 12th fret, you can barely touch your finger and you'll get this very interesting overtone, and the overtone will be the same tone as the tone of the string vibrating on its own, and that is represented in this diagram right in the middle, you see? And here is an actual guitar. Notice that it came from Pythagoras, so an ancient guy started showing us this string movement. And you see right there in the middle, it's the half point, and then some of the other places, like the fourth, is right there at the 3/4 mark. The 2/3 mark is the fifth in the tonal category. Fractals. In the summer of 2009, we were living in West Virginia on Cherry Street in Hurricane. I had a membership at the local library and I got into fractals. Our oldest was a 2-year-old at the time, so we had a non-ending supply of sidewalk chalk, and I would get out there in the driveway at our rental home and draw fractal designs, trees, plants, leaves. There are other fractal designs, but they are represented very strongly in nature. Which is a good transition point into the golden ratio. The golden ratio, also the Fibonacci set, is a very cool thing that has legs in the art world and the math world. The Fibonacci set, each subsequent number is the sum of the previous two, and what it does is it brings a pattern. Here's the pattern in a block form, then it keeps on spiraling, and it does spiral. This is what the spiral ends up looking like. The shape that you see so frequently in nature. In architecture, art evaluations also use it. The Fibonacci sequence, or something very close to it, is also a seed and flowering pattern. It's very cool to see how many ways it sticks around in nature. There's math in art. M.C. Escher was a philomath who transferred his art abilities onto paper and canvas by these familiar popular paintings showing order and pattern and repetition. Math and quilts. This one's one of my favorites since I'm a quilter. Mathematics showed up in the Middle East with Muslim architecture. Really pretty, really good, great tile work. Comes from the tessellations and connecting the right dots at the right place on the geometric figures. A lot of people have heard about pi, but have you ever heard about phi? Phi is another really cool ratio that you've got to look into. It's so cool. Closely related to the Fibonacci sequence. As you see here, if starting by 1 over 1, add the numerator and the denominator of the first equation, making this number the numerator of the next fraction, and the denominator the integer from the previous one, and as you proceed, the product draws closer and closer to the Phi ratio. I've played with this Phi ratio a lot. It's still so hard to wrap my mind around the concept, but it's really simple. So I'm going to get the text of this brief description from goldennumber.net. Phi is simply the ratio of line segments that result when a line is divided in one very special and unique way. Divide a line so that the ratio, the length of the entire line, A, to the length of the larger line segment, B, is the same as the ratio of the length of the larger line segment, B, to the length of the smaller line segment, C. This happens only at the point where A is 1.618 times B, and B is 1.618 times C. Alternatively, C is 0.618 of B, and B is 0.618 of A. What makes phi even more unusual is that it can be derived in many, many ways and shows up in the relationships throughout the universe. Phi ratio appears in the human body, in other animals, in the Bible, the stock market, and other statistical models. It's everywhere. Closely related to the Phi ratio are the proportions of the human body. We're going to drop in on Brett doing some research on proportions now. Let me see who this guy is. Oh, that's not it. Cabossier. Yeah, Cabossier. You've seen the guy. Here it is. You've seen this guy, and that's from Da Vinci. Well, there was another guy. You know, this is the ratio of the human body, and it's based upon some of the basic geometry of the circle, the square, and the triangle, and then Le Corbusier had more formulas worked out with the human figure, and you see this beautiful little spiral here, and it's based upon ratios. And he was an architect, and he applied ratios to architectural design, which is not a stretch at all in ancient times, but it's like an art that has been lost in our day and age. So he was just kind of reviving something by using ratios, like how you size a door, how you size the size of the floor. And I think we've just taken a mean average and gone with that, 8-foot ceiling, rather than make it an actual ratio of the people who would occupy the place. A lot of these concepts may seem complex, so let's look at a few simple models. Square. And speaking of Pythagoras, this is a cool graphical representation of the Pythagorean theorem. On-ramps of enjoying math could be in simple machines. Things like screws and ramps and levers and all kinds of different ancient tools. Simplicity can end up shifting right into the complex. What looks like just a bunch of lines on a page, this is the kind of math that they use to make cell phone antenna technology created by an Israeli mathematician.
And now for some interesting number patterns.
That's really the draw of discovering a friendly relationship with math, which school often kills, but like some people can fall back in love with art later in life after it's killed in school, so can math be resurrected. Hey, if you liked it, I have other videos kind of like this from this math series. Okay, that's it.